The hum of machinery filled the cavernous assembly hall, punctuated by the occasional clang of steel striking steel. Frank Ainsworth adjusted his safety goggles and stepped cautiously between rows of half-assembled M4 Sherman tanks. He was a civilian engineer, plucked from the automobile industry by the War Production Board 6 months prior, now thrust into a world where the stakes were measured in lives rather than car sales. Detroit was a city transformed. Once the heart of consumer automobiles, it now pulsed with wartime urgency. Here, the factories did not produce luxury, they produced survival. Frank, 35, of medium build and steel-grey eyes, had spent a decade managing assembly lines at Packard Motors. Efficiency was his language, flow his religion, and precision his obsession. Yet nothing in his years of overseeing luxury sedans had prepared him for this. The M4 Sherman was a marvel of engineering in concept, but in practice it was a slow-moving beast. Each tank required hundreds of man-hours, and the factory floor was a choreography of missteps, redundancy, and frustration. Workers shuffled between stations, often waiting for parts that had not yet arrived, while supervisors barked instructions over the roar of engines and welding torches. "Look at this," Frank muttered under his breath as he watched 2 teams wrestle a turret into position. "They're losing hours just aligning those bolt holes." A nearby foreman, a wiry man named Simmons, grunted in acknowledgement. "We've tried to speed it up, engineer, but the process, it's just how it's always been done. Army says one misaligned turret and it's our heads." Frank nodded, but his mind raced. This was exactly the problem. The assembly process was sequential. The hull completed first, the engine installed next, the turret last. Each stage depended entirely on the previous one. Any delay cascaded, leaving the rest of the workforce idle. The result? Weeks to complete a single tank, despite hundreds of men and women working in shifts around the clock. The pressure from Washington was relentless. Intelligence reports from North Africa and soon Sicily painted grim pictures. German Panther and Tiger tanks dominated the battlefield. The M4 Sherman, while reliable and mechanically robust, was outnumbered and often outgunned. Military planners demanded more tanks, faster. The War Production Board had set a target that seemed impossible, cut assembly time by half. Frank's assignment, whispered in the initial meetings with army officers and production managers, sounded like a cruel joke. "We need someone to make the impossible happen," one officer had said. "Half the time. Double the output." The room had gone silent, save for the ticking of a wall clock. It was not just a matter of schedules. Military officials were deeply conservative, favouring methodical, step-by-step production. Any deviation from the standard procedure was treated with suspicion. Frank, a civilian with no combat experience, was seen as a risk. His ideas, radical concepts drawn from automobile assembly, would be scrutinized and likely resisted. He was entering an environment where efficiency and tradition were at war. Frank moved along the line, noting every inefficiency with a meticulous eye. The hull assembly station, where heavy steel plates were welded, was a bottleneck. Workers paused frequently to check measurements manually, despite templates available but unused. Nearby, a group of machinists installed suspension components, interrupted by missing bolts that had been delayed from the parts department. On the far end of the hall, electricians struggled to wire the engine systems, often having to backtrack because engine mounts were not perfectly aligned. He scribbled notes in a small leather notebook, a habit he had maintained since his early days in Detroit. Redundant steps, misaligned workflows, underutilized machinery. He catalogued them all. Every idle minute represented a tank delayed, every misstep a frontline soldier potentially left unsupported. During lunch, he walked past the cafeteria where workers, grease-stained and weary, murmured about the relentless pace. "We've been doing it this way since '40, one welder said, shaking his head. "Nothing's going to change." Frank didn't respond. Change, he thought, would have to be subtle and systemic, not loud or confrontational. By mid-afternoon, he convened a small group of engineers in a quiet corner near the tool storage. Using his notebook, he began sketching diagrams. He demonstrated how overlapping certain tasks could save hours. Hull assembly could be prefabricated in sections, while turrets were simultaneously assembled on parallel tracks. Engine installations could be streamlined using standardized jigs rather than hand-measured templates. Each illustration revealed time that could be reclaimed, but skepticism was immediate. Colonel Harding, sent from the Army's Ordnance Department, crossed his arms. "This may work on paper, Mr. Ainsworth, but our men are trained to follow procedure. Any shortcuts and the tank might fail in combat. Half measures aren't acceptable." Frank met Harding's stare. "Sir, it's not about shortcuts. It's about structure. We're not compromising integrity, we're reorganizing workflow. If done correctly, each tank will be built faster, safer, and with fewer mistakes. Right now, we're wasting hours every single day on avoidable delays." Harding shook his head. "We'll see. I don't want to gamble with soldiers' lives." That evening, Frank returned alone to the floor, walking among the idle machinery as the last workers filed out. He imagined a line where sections moved in parallel, where every welder, rigger, and machinist contributed simultaneously to the final tank. He envisioned time reclaimed, hours slashed, output multiplied. It was ambitious, perhaps audacious. But if he succeeded, it would be the difference between a steady stream of tanks to the battlefield and critical shortages in North Africa. Frank stopped before a half-assembled Sherman, its turret dangling awkwardly above the hull. He ran a hand along the rough metal and whispered to himself, "There's a better way. And I'll find it." By the time the factory lights dimmed, Frank had begun sketching the first detailed plan for what would later be called the modular assembly approach. It was a civilian's solution to a military problem, audacious in conception and, for now, utterly untested. Yet in the shadows of Detroit's sprawling tank plant, the seed of innovation had been planted. A seed that, if it took root, would shorten production time from weeks to days and, unknowingly, help tip the balance of the war. Frank Ainsworth walked past the towering smokestacks of the Lockheed Detroit tank assembly plant, the hot summer air thick with oil and exhaust. Inside, the hum of machinery was both deafening and mesmerizing, a symphony of wartime industry. The problem on the floor had become clear. Sequential assembly was choking production. Each Sherman tank took far too long to complete, each delay rippling through the lines like a domino chain. The War Production Board's targets hung over Frank like a guillotine: 50% faster production or face scrutiny from generals who rarely tolerated failure. Yet Frank wasn't new to this. He had spent 10 years immersed in the lessons of Detroit's auto factories, observing the genius of Henry Ford's assembly line and the staggering efficiency at Ford's Willow Run B-24 bomber plant. Both were marvels of organization and innovation, tasks broken into small, repeatable units, workers trained to perform one operation flawlessly and repeatedly. Prefabricated components moved along tracks, arriving at each station in perfect sequence. He stopped before a mock-up Sherman hull mounted on a rotatable stand. Frank ran a gloved hand along the cold steel. "It's all about flow," he muttered, thinking aloud. "Flow and modularity." The concept had come to him one sleepless night. What if tanks, like automobiles, could be assembled in modules? Rather than constructing a tank from start to finish sequentially, separate sections, hull, turret, engine compartment, suspension, could be built simultaneously, then joined at the final stage. Workers would no longer wait for parts. Machines would no longer sit idle. Time reclaimed, productivity multiplied. The next morning, Frank met with Colonel Harding and the plant's military production supervisors. They gathered in a small, stuffy office stacked with blueprints and charts. Frank spread out his sketches on the table. Diagrams of parallel assembly tracks, standardized jigs, and prefabricated sections ready to converge into a finished tank. "Here's how it could work," Frank began, pointing to the drawings. "Hull sections are welded in separate bays. Suspension assemblies are pre-installed. Turrets are assembled concurrently. All parts converge on the final line, synchronized to meet perfectly. We're talking days instead of weeks." The room went silent. Harding's face, usually unreadable, betrayed a flicker of doubt and curiosity. "And you're certain this won't compromise armor integrity?" he asked. Frank nodded firmly. "I've tested this on scale models. Alignment can be guaranteed with proper jigs. Armor thickness, welding standards, engine mounts, all remain consistent. Nothing is sacrificed. We're simply reimagining the workflow." Major Reynolds, a grizzled engineer who had spent the last decade in Army ordnance, leaned back. "Mr. Ainsworth, your ideas are unusual. This isn't a car factory. A Sherman is a weapon of war. If a turret falls off in combat, the blame isn't yours. It's ours. Efficiency is fine, but reliability is non-negotiable." Frank pressed on. "Reliability is paramount, but there's a difference between doing the same thing slowly and doing it efficiently. At Willow Run, B-24 bombers were being produced faster than ever imagined because tasks were broken down and executed in parallel. Why can't the same principle apply to tanks?" The tension in the room was palpable. Civilian methods clashed with military tradition. Yet Frank's conviction began to chip away at skepticism. He returned to the factory floor that afternoon, accompanied by a small team of engineers and foremen who had agreed, cautiously, to experiment with his modular approach. Frank had prepared a series of mock-up assemblies, a partial hull, a pre-installed engine compartment, and a separate turret. Each section was deliberately oversized and adjustable, allowing teams to test alignment, fit, and welding processes. At the welding bay, Frank instructed a team of operators to attach prefabricated hull plates using newly designed jigs. Sparks flew as torches danced over steel seams. Unlike the previous sequential process, the hull sections could now be welded simultaneously in multiple bays. The speed was dizzying. Meanwhile, the turret team experimented with mounting the main gun and periscopes in isolation from the hull. Technicians discovered that working on the turret independently allowed for precision adjustments that were often compromised when welded last on the traditional line. Electrical wiring, communication systems, and gun controls were tested in parallel, ensuring functionality before final assembly. Frank observed the process, jotting notes furiously. "The concept works," he said under his breath. "If we scale this, the savings will be monumental." By midweek, the team had successfully joined a prefabricated hull, engine compartment, and turret into a single, fully functional Sherman mock-up. The fit was near perfect, and the welding integrity met Army standards. Frank's modular method had already demonstrated the potential to cut assembly time by nearly 40%, without compromising quality. Word of the success spread slowly through the plant. Some supervisors remained skeptical, their loyalty to tradition deeply ingrained. Others began to see the promise. One young welder, barely 20, whispered as he adjusted a turret mount, This is amazing." We could actually finish more tanks than anyone thought possible. Frank knew this was only the beginning. Modular assembly required more than mock-ups. It demanded retraining workers, reorganizing production bays, and coordinating supply chains to deliver components precisely when needed. The logistical challenge was immense, but the potential gains were irresistible. He began drafting a phased implementation plan, detailing the resources required, workflow adjustments, and quality checks at every stage. That evening, Frank walked alone past the factory's towering cranes and unfinished Sherman hulls. He recalled Henry Ford's famous words, "Quality means doing it right when no one is looking." Here, in Detroit's tank factories, the principle was no less true. Efficiency and speed were vital, but only if the resulting machines could survive the battlefield. The sun set behind the smokestacks, casting long shadows across the assembly floor. Frank paused, gazing at a partially assembled turret gleaming in the fading light. He knew the military would not immediately embrace his ideas. Conservatism and tradition ran deep. But if he could prove that modular assembly worked, the implications were staggering. The US Army could receive tanks faster, front-line units could gain numerical parity, and lives could be saved. For the first time, the impossible challenge did not feel so impossible. In the echoes of Detroit's factories, amidst the roar of machines and the scent of molten steel, Frank Ainsworth saw a path forward, a civilian's innovation bridging the gap between industrial expertise and military necessity. A seed had been planted, and soon it would grow to reshape how America built its tanks, changing the course of the war itself. The morning sun had barely crested over Detroit's industrial skyline when Frank Ainsworth returned to the Lockheed assembly plant, clipboard in hand and determination in his eyes. Weeks of planning had led to this moment, the first trial of the modular assembly system in real production conditions. The plant hummed with activity, the clatter of machinery and the hiss of welding torches forming a rhythmic backdrop. Workers, some curious, some skeptical, glanced at Frank as he strode down the centre aisle. Colonel Harding and Major Reynolds awaited him near the newly constructed test bay. Both men bore the stiff posture of military oversight, their expressions betraying a mix of anticipation and doubt. "Remember, Ainsworth," Harding said, folding his arms, "we're counting every day. If this fails, it isn't just theory. It's wasted resources, delayed deployment, and potential casualties on the front." Frank nodded. "Understood, sir. That's why we've run multiple simulations. Today we put theory into practice, and I'm confident the results will speak for themselves." The first tank slated for trial was designated T421. Its hull had been prefabricated in a separate bay, the suspension assembly completed independently, and the turret fully constructed with main gun and electrical systems installed. Normally, this entire process required nearly 6 weeks. Today, the goal was to complete it in less than 10 days, a pace previously deemed impossible. As the shift began, Frank monitored the movement of components. Cranes lifted hull sections onto the main assembly track, guided by operators trained to position them precisely. The suspension units, engines and turrets followed in timed sequence, arriving exactly when needed. In theory, parallel work should eliminate idle time. In practice, small errors could cascade, and the military supervisors watched every step with hawkish eyes. A minor misalignment occurred almost immediately. One of the turret's hydraulic mounts didn't match the pre-drilled hull interface perfectly. Welding operators froze. Frank approached the station, assessing the situation. "This is expected," he said calmly. "Small adjustments are part of the process. The jigs are designed to correct minor deviations without compromising integrity." He directed the crew to loosen the mount slightly, realign the turret, and secure it in place. Within minutes, the problem was resolved. Harding's frown softened into a nod of approval. "Well, that's faster than usual troubleshooting," he admitted. The day progressed with a mixture of tension and cautious optimism. Workers moved components with precision, guided by new floor markings and standardized instructions. Technicians tested electrical connections and hydraulics on the turret while the hull was being finalized. Engines were installed in parallel, eliminating the bottleneck that had plagued traditional assembly. By mid-afternoon, T421 was nearly complete. Yet skepticism lingered. Major Reynolds remained watchful, occasionally muttering under his breath about the risks of unproven methods. "If the armour fails in the field, Ainsworth," he warned, "we'll be held accountable. Speed is meaningless if the tank can't survive one hit." Frank welcomed the scrutiny. Quality assurance had always been his priority. He instructed his team to perform rigorous stress tests before final assembly. Weld seams were inspected under magnification, hydraulic systems underwent pressure tests, and engine mounts were subjected to simulated vibrations. Every component met or exceeded Army specifications. By the evening, the final stage arrived, joining the separately constructed sections into a single operational tank. The hull, turret, and engine compartments slid into place like pieces of a mechanical puzzle. Welding torches sealed seams, hydraulic lines were connected, and the tank's electrical systems came online. Frank's heart raced as he watched the indicators flicker and stabilize. Colonel Harding circled the vehicle, his hands clasped behind his back. "Remarkable," he finally said. "The fit, it's perfect." "And the timeline? How long did this take?" Frank consulted his notes. "From start to finish, 8 days, sir." "That's a reduction of nearly 90% compared to traditional methods." Harding raised an eyebrow. 8 days? That's impossible. Everyone said it couldn't be done." Frank smiled faintly. "Sometimes, impossible is just a challenge waiting to be understood." Despite the successful trial, the real test was yet to come, convincing military leadership to implement the method across multiple production lines. Frank presented his results to a small review board the following week, including representatives from the War Production Board and Army Ordnance. He laid out detailed charts comparing traditional sequential production to his modular system, highlighting time savings, resource efficiency, and the maintenance of armor integrity. Not everyone was persuaded. One board member, a senior ordnance officer, shook his head. "Ainsworth, I respect your work, but this is unprecedented. Entire supply chains would have to be reorganized. We risk misalignment, delays, and potential battlefield failures. How can we be certain your method scales without catastrophe?" Frank leaned forward. "The risk of doing nothing is greater. Frontline units are demanding tanks faster than our current process allows. Modular assembly doesn't compromise safety, it enhances it. Parallel construction allows for independent testing, catching defects early rather than after weeks of labour." The debate continued for hours. Arguments about reliability clashed with discussions of efficiency, and Frank remained steadfast, armed with precise data, observations from Willow Run, and results from the T421 trial. By the end of the session, the board had not yet approved full implementation, but they had agreed to authorize additional pilot runs. It was a small victory, but a critical one. Back on the factory floor, workers whispered about the potential for change. "I've never seen a hull and turret come together this quickly," one welder said. "If Ainsworth's right, we might actually beat the Germans at their own pace." Frank spent the night reviewing every detail of the trial. Alignment errors, welding inconsistencies, minor delays. He catalogued each with suggestions for correction. This was no longer theoretical. Lives depended on the system functioning reliably under pressure. As he walked past the assembly bays, the newly completed T421 gleamed under overhead lights. The machine represented more than steel and mechanics. It was the embodiment of civilian ingenuity, industrial discipline, and relentless problem-solving. Frank understood the stakes. If his modular system could be implemented widely, American forces could flood battlefields with Sherman tanks faster than anyone believed possible. The war could hinge on these innovations, and the weight of responsibility settled on his shoulders like the steel plates of a tank. Yet amidst the doubt and skepticism, one fact remained unassailable. Frank Ainsworth had shown that what was deemed impossible could in fact be achieved. And with each small victory, the path toward revolutionizing American tank production became clearer. The metallic hum of Detroit's industrial heart seemed to echo Frank Ainsworth's own pulse that morning. The Lockheed plant, a sprawling complex of steel and concrete, was alive with the coordinated chaos of men, machines, and materials. Today marked the first formal military trial of the modular tank assembly system. Approval from the War Production Board had been partial, granting only limited pilot lines. But it was the first time the Army's generals would witness civilian innovation in full operation. Colonel Harding met Frank at the main entrance, his crisp uniform slightly rumpled from the early inspection tour. "Remember, Ainsworth," Harding said, a hint of tension in his voice, "the brass upstairs aren't used to seeing civilians dictate production methods. You'll need more than speed. You'll need to prove reliability under scrutiny." Frank nodded. "That's the plan, Colonel. Every tank leaving this line will meet or exceed specifications. The data speaks for itself." The generals arrived mid-morning, their black sedans rolling up through the plant gates. Brigadier General Samuel Eaton, a man with a reputation for rigid adherence to protocol, led the group. Beside him was Major General William Henderson, who had spent decades overseeing armoured divisions in Europe. Their eyes, sharp and evaluative, scanned the assembly floor. "Mr. Ainsworth," Eaton began, voice clipped, "we've been briefed on your methods. Parallel assembly, modular hulls, prefabricated turrets. We find it unorthodox. The Army demands proven methods. Our soldiers cannot risk mechanical failure because someone decided to speed things up." Frank swallowed, steadying his voice. "Sir, I understand your concern, but traditional sequential assembly is too slow to meet current demand. Modular construction doesn't compromise structural integrity. In fact, it allows for independent quality checks on each section before final integration." Henderson's gaze lingered on a nearly completed Sherman rolling down the line. 8 days, he muttered. 8 days from raw components to finished tank. It's almost unbelievable. Frank gestured to the line. "We completed the T421 in 8 days last trial. Today we have 3 more tanks underway, and each follows the same method. I'd like to show you the process step by step." The generals followed as Frank led them past the hull bay, where giant presses shaped armoured plates. Workers moved in coordinated choreography, welding, fitting, and inspecting each section with precision. Modular sub-assemblies glided along the floor on specialised tracks, arriving at the main line in perfect sequence. Eaton's scepticism was palpable. "How do you account for misalignment when sections are produced separately?" he asked. Frank stopped beside a hull being joined with its turret. "We use precision jigs and alignment guides. Minor deviations are corrected before integration. Every weld and hydraulic connection is tested independently. In a conventional line, these errors are discovered only after weeks of labour. Modular assembly identifies and resolves them immediately." Henderson, who had spent the war inspecting armoured units in combat zones, leaned closer. "And you're confident these tanks can withstand field conditions?" "We can't afford early losses due to untested processes." Frank gestured to a nearby stress testing station. "We conduct vibration, hydraulic and armour stress tests on every component before final assembly. Additionally, parallel production allows rapid replacement of defective sections without delaying the overall schedule." The generals moved to the final integration station. A turret descended smoothly onto a hull, guided by crane and alignment rails. The welders sealed the connection in minutes, while technicians connected hydraulics and electrical systems. Within hours, a fully operational Sherman emerged, gleaming under the factory lights. Eaton crossed his arms, visibly impressed despite himself. "It's faster than I imagined, but scale remains a concern. How do you intend to replicate this across multiple plants?" Frank had anticipated this question. "We start with pilot lines, training crews in modular assembly. Once proven, standard jigs, tools, and procedures allow other plants to replicate the method without disrupting existing supply chains. It's not experimental. It's a controlled, scalable process." Despite Frank's assurances, resistance was deeply entrenched. Army logistics officers worried about retraining workers and managing new material flows. ordnance officials fretted over the potential for missed inspections or integration errors. Meetings stretched late into the evening, arguments punctuated by Frank's unwavering calm and meticulous data. By the end of the day, a compromise emerged. The generals approved expansion to 2 additional pilot lines, with strict oversight and daily reporting. It wasn't full-scale implementation, but it was a victory, the first formal recognition that civilian engineering could influence military production. Back on the floor, Frank walked among the workers, observing their reactions. Some whispered in disbelief at the speed of production. Others murmured questions about new techniques or shared lessons from previous assembly experiences. Frank encouraged experimentation within controlled parameters, understanding that worker buy-in was essential for long-term success. That night, Frank stayed late, reviewing reports and noting minor inefficiencies observed during the trial. Conveyor timing, welding sequences, and component delivery all required fine-tuning. Even small improvements could shave hours off the process and further validate his methods to military superiors. Amid the bureaucratic tension, a quiet sense of momentum grew. The trial had proved that speed and quality need not be mutually exclusive, and that innovation could triumph over convention when rigorously applied. The Army's initial resistance had softened, replaced by cautious curiosity, and the understanding that in a war where every day mattered, even impossible ideas warranted serious consideration. Frank paused at the end of the shift, gazing at a line of nearly completed Shermans. Each tank represented more than steel and machinery. They embodied civilian ingenuity, industrial discipline, and the potential to alter the pace of the war. It was clear the next challenge would be scaling this system, navigating military bureaucracy, and ensuring every tank leaving the line could survive the unforgiving battlefields abroad. For Frank Ainsworth, the impossible was no longer theory. It was reality in motion, and the war's outcome might just depend on it. Winter arrived in Detroit with a biting chill that seeped through the steel beams of the Lockheed plant. Outside, snow blanketed the city streets, but inside, the factory floor hummed with relentless activity. The pilot line trials had proven the concept. Modular assembly worked, and it worked quickly. Now came the true test, scaling up production without sacrificing quality or introducing chaos. Frank Ainsworth moved among the machinery and workers with the ease of a conductor leading a symphony. The pilot line had been small, limited to a single hull and turret combination. Scaling meant replicating the system across multiple lines and plants, coordinating hundreds of additional workers, and managing an influx of components that threatened to overwhelm even the most seasoned logistics officers. Colonel Harding visited in mid-December, clipboard in hand, his expression a mixture of approval and lingering concern. "Ainsworth, I've reviewed your new staffing plan. You're proposing to train over 400 additional workers in modular assembly within a month. Are you confident this won't disrupt the existing supply chains?" Frank's voice was steady. "Sir, the key is standardization. Every jig, every crane, every workstation follows the same sequence. Workers learn their module, master it, and then replicate it elsewhere. It's not chaos, it's controlled redundancy." The first challenge arose immediately: recruitment and training. Detroit's workforce had grown accustomed to conventional sequential assembly. Hundreds of men and women, many drafted from other industries or newly arrived from rural areas, now faced a method they had never seen. Frank established an intensive training program. Instructors led small groups through mock assembly exercises, emphasizing precision, speed, and error detection. Each worker became responsible for a single module, one focused on hull welding, another on turret hydraulics, another on armor plating. By isolating tasks, the plant could parallelize work like never before. Major General Henderson toured the lines, skeptical yet intrigued. "I've inspected tanks in Europe," he remarked. "I've seen hundreds of failures from rushed production. How do you ensure that speed doesn't compromise survivability?" Frank guided him past the inspection stations. Every module undergoes rigorous testing before integration. Hulls are stress-tested, turrets calibrated, hydraulics examined under maximum pressure. If a defect is found, it is corrected immediately without holding up other modules. Parallel production allows simultaneous troubleshooting. Despite meticulous planning, scaling introduced unforeseen problems. Component delivery was inconsistent, forcing workers to improvise. Some parts arrived days late, others were mismatched due to minor specification errors. Frank quickly implemented a color-coded tracking system and standardized labeling, ensuring each component reached its designated module at the right time. Union representatives expressed concern over worker fatigue and repetitive strain. Frank worked with plant supervisors to rotate shifts and balance workloads, maintaining productivity without compromising safety. He also introduced incentive programs, small rewards for teams that met production and quality targets, which boosted morale on the factory floor. By mid-January 1943, the first full-scale production lines were operational. 3 lines now operated simultaneously, each capable of producing a Sherman tank in 8 days. The output far exceeded the Army's initial projections. Military inspectors arrived regularly, recording data and verifying compliance with specifications. While initial visits were tense, the consistent quality of completed tanks gradually silenced criticism. One afternoon, Frank received a call from Washington. A War Production Board official informed him that additional plants across the Midwest were interested in adopting the modular system. Suddenly, what had begun as a single experiment in Detroit was on the verge of nationwide implementation. The challenge now was coordination. Each plant had unique layouts, machinery, and workforce composition. Frank would need to standardize procedures while allowing flexibility for local conditions. He traveled extensively over the next months, moving between Detroit, Chicago, and Toledo. At each site, he trained supervisors, set up jigs and cranes, and ensured the integrity of supply chains. The Army monitored his progress closely, sending liaisons to document successes and report back to generals in Washington. Resistance persisted, particularly from traditionalists within the Ordnance Department. Some officers argued that civilian methods, while innovative, might fail under wartime stress. Frank countered with data. Defect rates on the modular lines were lower than those on conventional lines, and production velocity had increased threefold. Charts, photographs, and first-hand observations became his weapons in bureaucratic battles. By March 1943, production was scaling beyond initial expectations. What had been a single pilot line in Detroit had grown into 6 fully operational lines across 3 states. The average tank assembly time dropped from 35 days to 8, effectively reducing construction time by nearly 75%. The Army's armoured divisions would soon have access to a quantity of Shermans previously thought impossible. Amid the triumph, Frank remained vigilant. Scaling production was not simply a matter of replicating processes. It required continuous monitoring, refinement, and worker engagement. Small inefficiencies, if left unchecked, could multiply across multiple plants, eroding the gains of modular assembly. Frank instituted daily review meetings, where supervisors presented production statistics, discussed obstacles, and shared innovative solutions. On one particularly cold March morning, Frank walked the line, observing tanks glide from hull assembly to final integration. He watched as workers applied the finishing touches, tightened bolts, and tested systems with precision honed over months of training. For the first time, he allowed himself a brief moment of satisfaction. The impossible had become reality. Tanks that once took weeks now rolled off the line in just over a week, ready for shipment to the front lines. Yet even in success, Frank knew the war demanded more. German armoured divisions were evolving, and the Allies would need sustained, uninterrupted production to maintain parity. His task was far from complete. Scaling had been achieved, but innovation would continue to drive the pace of victory. By the time the first modularly produced Sherman tanks rolled off the Detroit lines in March 1943, the tide of armoured warfare in North Africa was reaching a critical juncture. The US Army's Second Corps, newly equipped with M4 Shermans, prepared for an offensive against entrenched Axis positions in Tunisia. Intelligence reports indicated that German forces, fielding Panzer IIIs and IVs, had the numerical advantage in certain sectors. Yet the arrival of freshly assembled Shermans offered a new strategic variable: quantity combined with reliability. Frank Ainsworth followed developments closely from Detroit, reading daily dispatches from the front lines. He was both anxious and exhilarated. He had spent months refining assembly, optimizing workflows, and troubleshooting bottlenecks. But now his work would face the ultimate test: combat. The first shipment of 20 tanks arrived at Bizerta harbour. Crewmen, hastily trained yet competent, inspected each unit. They were struck by the consistency. Welds aligned perfectly, turrets rotated smoothly, hydraulics functioned without delay. Reports from pre-combat drills indicated a marked improvement over previous Sherman batches, which had occasionally suffered minor mechanical failures during transit. Lieutenant Colonel James "Jimmy" Reynolds, assigned to lead one of the first Sherman companies in Tunisia, wrote in his field diary, "I've inspected these tanks more thoroughly than any I've seen before. Every hull is solid, every turret responsive. The men trust them immediately, which is half the battle won." On April 10, 1943, the first engagement occurred near the hills outside Kasserine Pass. Axis forces had established a series of fortified positions, reinforced with mines and anti-tank obstacles. The Sherman units, previously constrained by limited armour availability, now advanced in greater numbers, enabling coordinated flanking manoeuvres. Frank read the initial reports with a mixture of disbelief and pride. Despite facing seasoned German crews, the Shermans demonstrated reliability and tactical flexibility. Units could sustain prolonged engagements without frequent maintenance stops, a direct result of the modular production process, which had allowed tighter quality control during assembly. Combat analysts later noted that the increased production rate directly influenced operational strategy. Whereas previously commanders had rationed tanks carefully, the surge in available Shermans enabled simultaneous offensives across multiple sectors. This forced the German command to spread their armour thinner, reducing the concentration of force at critical points. In mid-April, the 1st Armoured Division launched an attack on a heavily defended Axis supply route. Sherman platoons, supported by mechanized infantry, advanced in waves. Tanks assembled in Detroit reached the front line within weeks of completion, a logistical feat that had previously taken months. Corporal William Hargrove, a tank gunner, recounted his first battle. "I climbed into my Sherman, and I swear it felt like it had been made for this moment. Everything moved right. The turret didn't stick. The gun fired smooth. We could maneuver faster than anything I'd been in before. I didn't have to worry about breaking down in the middle of a firefight, and that gave us the edge." The tactical outcomes were striking. Allied units equipped with modularly produced Shermans managed to seize multiple strategic positions in fewer days than predicted. The ability to replace lost or damaged tanks quickly meant that offensives could be sustained continuously, a decisive factor in the overall campaign. Meanwhile, German field reports began to take note. Reconnaissance noted a sharp increase in the number of American tanks, and intelligence analysts remarked on the unprecedented consistency in performance. Units that had relied on staggered, sequential production were now faced with an opponent whose armoured strength could be replenished at an almost industrial pace. The War Department took note of the impact. High-level memos praised the Detroit Modular Initiative, recognizing it as a force multiplier that extended beyond mere numbers. By increasing both production and reliability, Frank's approach allowed commanders greater strategic flexibility and reduced attrition due to mechanical failures. By May 1943, the cumulative effect was undeniable. Axis positions in Tunisia weakened under sustained pressure, and Allied forces captured key towns and supply hubs. Field reports credited not only tactics and infantry performance, but the sheer availability of reliable armour. Tanks that once would have taken over a month to replace could now be delivered in a fraction of the time, maintaining operational momentum. Back in Detroit, Frank and his team followed these developments with a quiet sense of accomplishment. He visited the assembly lines daily, walking past the massive hulls, armoured turrets, and welding stations. Each completed Sherman represented not only a machine of war, but a testament to the principles he had championed: efficiency, standardization, and controlled innovation. Yet Frank remained cautious. Early success did not guarantee long-term victory. Combat environments were unpredictable, and lessons learned on one battlefield might not apply elsewhere. He continued refining assembly methods, experimenting with component standardization, and liaising with military engineers to anticipate future armoured needs. By June 1943, as the North African campaign drew to a close, the influence of Frank's innovations was clear. Sherman tanks produced through modular assembly had accelerated the pace of engagement, reduced downtime, and allowed the Allies to field a numerical advantage previously deemed impossible. Strategic analysts credited production methodology as a critical factor in maintaining frontline momentum, a rare acknowledgement for a civilian engineer working behind the scenes. Frank would later recall that period not in terms of numbers or charts, but by the human dimension: the crewmen who trusted the tanks, the foremen who mastered the new assembly process, and the military leaders who adapted their tactics to a sudden surge in armoured capability. His impossible trick had not only transformed industrial production, but reshaped the battlefield itself. By the summer of 1943, the initial success of modular tank production had been proven on the battlefield, but Frank Ainsworth knew that victory in combat was only half the battle. The real challenge lay in refining the process, scaling it nationwide, and ensuring that what had been an impossible civilian innovation could survive the rigors of wartime demands. Back at the Detroit assembly plant, Frank walked the production floor with a clipboard in hand, noting adjustments in workflow and machine utilization. He had spent months observing bottlenecks, redundant steps, and uneven workload distribution. Even with the modular approach, some sections lagged behind others, creating inefficiencies that threatened to slow the output of complete tanks. Frank had learned an important lesson early on. Innovation alone was insufficient without continuous monitoring and adaptation. The modular system had allowed parallel assembly of hulls, turrets, and drivetrain components, but synchronization between teams was critical. A delay in one sub-assembly could halt the entire final assembly line, undoing the time savings the system promised. To address this, Frank implemented what he called the Assembly Sync Protocol. Each sub-assembly team reported hourly on their progress via a simple yet effective system of coloured flags and whiteboard charts. Supervisors, trained in basic engineering oversight, coordinated handoffs and flagged potential delays before they cascaded into full line stoppages. The system was crude by modern standards, but it worked. Tank output increased steadily, and production errors decreased significantly. Meanwhile, word of Frank's success had reached other major war production centres. Factories in Buffalo, Chicago, and even the West Coast began adopting similar modular principles, tailored to local facilities and workforce capabilities. Civilian engineers like Frank were brought in as consultants, and a culture of controlled experimentation emerged. Each plant tested small-scale mock-ups before full-scale implementation, ensuring that innovations did not compromise quality or safety. Military oversight, initially skeptical of civilian methods, gradually shifted. Brigadier General Samuel Cartwright, a long-time production supervisor, admitted during a conference call in July 1943, "We were worried that civilian shortcuts would compromise armour integrity. But the Detroit models proved otherwise. The tanks are sturdy, the crews trust them, and the rate of production is extraordinary. We must standardize these practices across all plants. Frank's team also focused on component standardization, a lesson drawn directly from his automotive background. Rather than producing dozens of slightly different parts that required manual fitting, engineers redesigned components to strict tolerances, allowing them to be interchangeable. Welds, bolts, and turret mounts were standardized, reducing errors and training time for assembly workers. This approach mirrored the principles used in Ford's automobile assembly lines decades earlier, but had never been fully applied to armored vehicles at such a scale. In addition to technical improvements, Frank recognized the importance of workforce training. Many assembly line workers were new to heavy industry, drawn from cities, farms, and small towns under the war mobilization effort. To ensure consistent quality, Frank introduced a rotational system where new hires shadowed experienced workers, mastering specific subassemblies before moving to more complex tasks. Combined with clear instruction manuals and visual diagrams, this system reduced mistakes and allowed the workforce to operate at peak efficiency. By late 1943, the results were remarkable. Average Sherman tank assembly time had dropped from the previous multi-week schedule to a mere 10 days from hull to battlefield-ready vehicle, a reduction of nearly 90% compared to pre-modular methods. Production forecasts now allowed planners to anticipate replacement schedules and allocate tanks to multiple theatres simultaneously, rather than concentrating resources in one area at the expense of another. The impact extended beyond the factory floor. Frontline commanders could plan more ambitious operations, confident that losses could be replaced rapidly. The North African campaign had demonstrated this principle. The availability of consistent, reliable armour directly influenced tactical decisions, enabling faster advances and sustained offensives. Frank himself remained humble about the recognition he received. While military reports, congressional hearings, and War Production Board memoranda highlighted the success of modular assembly, he continued to focus on incremental improvements. In his notes from August 1943, he wrote, "We have done well, but the system is only as strong as its weakest link. Every team, every machine, every supervisor must remain vigilant. War is unpredictable. Our work must be consistent, not just fast." By autumn, the lessons learned in Detroit and other plants began to influence post-war planning. Industrial historians later noted that the modular approach pioneered by Frank Ainsworth and his civilian colleagues became a blueprint for modern mass production of military vehicles. Techniques such as subassembly coordination, component standardization, and continuous workflow monitoring were studied and codified in training manuals for decades to come. The broader implications were also evident in workforce management. The emphasis on skill development, mentorship, and clear communication helped bridge the gap between industrial efficiency and human factors. Women and minority workers, who had entered the production workforce in unprecedented numbers due to the war, thrived under the structured training system, proving that large-scale industrial innovation could coexist with inclusive labour practices. On a personal level, Frank began receiving letters from tank crews who had fought in North Africa and Sicily. One, from Sergeant Michael O'Connell of the 1st Armoured Division, read, "Your tanks saved lives. We could count on them in battle, and that made all the difference. Thank you for making our job possible." These letters were rare and precious. They reminded Frank that his work was not an abstract exercise in efficiency. It had tangible consequences for soldiers risking their lives thousands of miles away. As 1943 drew to a close, Detroit's plants had become a model of wartime innovation. The combination of modular assembly, standardized components, and trained, coordinated labor had transformed tank production from a slow, cumbersome process into a near-continuous operation. The impossible trick that once seemed unlikely to succeed had proven its worth, shaping both the immediate outcome of the war and the future of American industrial engineering. Frank Ainsworth, a mid-level engineer drafted into service, had not only shortened production schedules, but had demonstrated a fundamental principle. Ingenuity, when applied systematically and combined with disciplined oversight, could overcome challenges that had once seemed insurmountable. The legacy of his work would endure long after the war, influencing armoured vehicle production, industrial strategy, and the very way engineers approached complex problems under pressure. By the first months of 1944, the impact of modular production had reached every corner of the US war machine. What had begun as a single experiment inside a Detroit tank plant had evolved into a nationwide doctrine, a synthesis of civilian innovation and military necessity that reshaped how America built its war. Frank Ainsworth's ideas, once dismissed as too radical for wartime, were now standard reading in War Production Board memoranda and Army Ordnance training materials. Across the country, factories once plagued by inefficiency were now humming in synchronized precision. Detroit, Chicago, Cleveland, and Buffalo all reported record-breaking output. The Sherman tank, once an industrial bottleneck, became a symbol of America's capacity to translate intellect into material power. Between January and August 1944 alone, over 6,000 M4s rolled off US assembly lines, a figure that would have been impossible without the modular system. The US Army's field reports noted a 40% reduction in mechanical breakdowns, and the replacement rate for combat losses improved by nearly twofold. From Washington, War Production Board officials watched these developments with cautious optimism. The early years of the war had exposed America's industrial weaknesses, shortages of machine tools, untrained labor, and scattered management. But by 1944, those same weaknesses had transformed into strengths, built upon the foundation of standardized work and streamlined assembly. Frank himself became an unlikely public figure. Though he remained stationed at the Detroit Arsenal, newspapers and radio broadcasts began referencing the engineer who made tanks flow like cars. Time magazine ran a brief feature in March 1944 titled The 10-Day Tank, crediting civilian ingenuity for the Allies' armoured surge. Frank was uneasy with the attention, but his superiors understood the symbolic value. America needed stories of problem solvers, civilians whose quiet brilliance fueled the war effort from behind the lines. Meanwhile, at the operational level, the benefits of mass-produced armour were transforming the battlefield. In Italy and the Pacific, commanders reported that entire armoured battalions could now be replenished in a matter of weeks. The logistical miracle was not simply in quantity, it was in consistency. A Sherman from Detroit fits seamlessly with a Sherman from Chicago or Cleveland. Spare parts, turrets, and tracks were interchangeable across theatres. Mechanics in North Africa could repair a tank built in Michigan with a shipment from Pennsylvania. This uniformity allowed the US Army's supply chain to evolve into a truly global system. Cargo ships carried modular tank components across oceans, where they were reassembled or repaired in field depots. The idea of modularity, once confined to factory floors, now extended to logistics and strategy. In February 1944, a War Department study titled Production Synchronization in the Armored Branch formally credited the modular assembly approach for eliminating 70% of redundant labor steps and reducing overall assembly-to-deployment time by 88%. It noted that the same principles were now being adapted by other branches, aircraft engine plants, naval shipyards, and artillery foundries. The study's conclusion was simple but profound. Standardization and parallelism are the engines of victory. At the National Defense Conference in Washington that spring, Frank was invited to present his findings alongside industrial leaders from General Motors, Ford, and Lockheed. His presentation was methodical, grounded in data rather than rhetoric. He displayed charts comparing pre-modular and post-modular production cycles, emphasizing how synchronization between civilian engineers and military oversight had been the decisive factor. General Brehon Somervell, head of the Army Service Forces, listened intently before addressing the audience. Mr. Ainsworth has demonstrated what this nation can achieve when the line between soldier and civilian disappears. The lesson here is not just how we build tanks, but how we think about building anything. Frank returned to Detroit that summer to find the plant almost unrecognizable. Automation aids, conveyor systems, and parallel assembly stations had multiplied. The floor buzzed with activity from thousands of workers, men and women alike, moving with practiced precision. The once chaotic clangor of metal and hammers now followed a measured rhythm like the pulse of an industrial symphony. Even the training schools had adapted. Young engineers studying in Chicago or Boston now learned the Ainsworth method, a term coined not by Frank but by a War Department publication summarizing his approach. It became part of the post-war curriculum at institutions like MIT and Purdue, blending production theory with the lessons of wartime urgency. Yet amid the accolades, Frank remained grounded. He often returned home late, exhausted but thoughtful. The war was far from over, and every improvement in efficiency meant more tanks and more lives placed at risk. In his private notes from June 1944, written days after D-Day, he reflected, "The better we build, the faster they fight. I can't stop thinking about that balance. Every hour we save here, somewhere a crew gains a chance to live or to die." His words captured the moral weight that many wartime engineers carried. Behind every statistic lay a human consequence. The modular assembly system had become an instrument of immense power, capable of sustaining entire campaigns, but also a reminder that innovation was not neutral. By late 1944, the Ainsworth system had been adapted for nearly every vehicle in the US arsenal: tank destroyers, self-propelled guns, amphibious tractors. The same philosophy guided the mass production of landing craft for the Pacific invasions. Even aircraft factories took cues from modular methods, dividing fuselage and wing production into parallel operations. What had begun as one man's response to inefficiency had evolved into a nationwide doctrine, a silent revolution in manufacturing philosophy. Industrial historians later described this transformation as the moment when America learned to fight with its factories as much as its armies. When the war finally turned decisively in the Allies' favour, Frank's name appeared only briefly in official reports. His innovation had been absorbed into the vast machinery of the American war effort, its origins obscured by the collective success it produced. But those who had worked beside him remembered.